Okay, we will talk about elimination as a process in general and with a focus on clearance and kinetic in this class. Okay, so let's start with the elimination. We mentioned before, or we know already, that the elimination as a kinetic process that involves excretion and metabolism. And we know that metabolism is irreversible change of the drug or loss of the drug to another entity, and for the excretion is the irreversible loss of the drug unchanged from the body. Okay, so we need a way to represent elimination and kinetic terms. Okay, so we will talk about this in this class, and we are still talking about first, oops, we are still talking about our model that we are having IV bolus with one compartment model, single dose, IV bolus, and linear kinetic or first order kinetic. Okay, so we are still talking about this model with its related conditions or assumptions. Okay, so what we will mention in this class is a general explanation of the elimination of this mod in kinetic in general with a specification to this model. Okay, earlier before when we started the explanation of this model, we mentioned that we can determine or describe the rate of elimination in terms of amount or in terms of concentration, measured concentration, right? So we had rate of elimination, right, as dx b over dt at certain time that was equal to minus k, which is elimination rate constant, multiplied to the amount remained in the body at certain time. And we were able also to use similar equation, okay, but in concentration term, because we know that the volume distribution is a constant term, and we were able to describe the same thing, the concentration at certain time over dt minus k multiplied with the concentration measured of the drug at certain time. Okay, in both of those cases, this is rate of elimination in amount terms, and this is rate of elimination in concentration terms, right? And again, for sure, we are still talking about first order kinetic. But the rate of elimination here is dependent, as we mentioned earlier, is proportionally related or directly dependent on the amount of the drug that is available in the body or remained in the body at time t. And similar thing here, the rate of elimination in concentration terms is dependent or directly proportionate to the concentration measured in the plasma, in this case at time t. Okay, which means as the amount is changing, as the concentration is changing, so the term that we are using to describe the rate of elimination here is not constant. Okay, So we need to find a way that is describing the elimination in a way that we can define the model accordingly. One way to do so is using volume per time to describe the elimination, okay, as volume per time, because we mentioned earlier that the volume that is we are using in this model is constant regardless of the drug concentration or amount of the drug in the body, right? So accordingly, the volume per time as a term would be constant. And this term, we call it the clearance of the drug. Okay? Again, because we are talking about linear kinetics, so whatever that we are mentioning here is true under linear kinetic or first order kinetic. The apparent volume of distribution is constant, okay, because it's not changing over time. And accordingly, the clearance is also constant because it's dealing with the volume of the biological fluid that have the measured drug in over time. Okay? And again, just to make sure that we know this, if we are talking about those both constants so far under first order kinetic, which also we are considering that we are having similar physiology and similar pathology in that individual that we are talking about when we are measuring the volume distribution or the clearance of the drug. Why is that? Because sometimes the volume distribution of the physiological condition is changing in the same individual or the pathological condition is changing, then it's not constant anymore. And this is one of the exceptions that we have in the kinetic. It's not linear anymore or it's not constant anymore because, for example, under some pathological condition, the body goes under continuous edema, which means that the volume of distribution or overall volume and the body is changing over time. So it's not constant anymore. So what we are having as two parameters so far that we are mentioning here under first order kinetic that we are considering that we are having normal states of the volume in different compartments in the body, and so it's not changing over time. So if the volume of distribution under those conditions is constant, so by default the clearance, the measured clearance is constant. And again, why we are doing that? Because we want to describe the elimination in a way or using a term or parameter that is constant, that defining the elimination of exact drug that we are studying or testing. Okay, so again, if you want to talk about the clearance as definition, is a measurement of the elimination of the drug regardless of the process, the exact process of it. It's elimination, so it could be related to metabolism or excretion or metabolism and excretion. Okay, so it's a measurement or description of the elimination of the drug from the body, regardless of the mechanism of the process that is happening in this elimination. Okay, we can have it as, or we can, the sample that we usually use for the clearance as CL or total clearance or systemic clearance. Okay, and again, if we are talking about um, those three symptoms, or some of the references may use different but similar symbols, we are talking about total elimination processes, either metabolism or excretion, or both of them, depends if the drug going under metabolism or excretion. Okay, and again, the unit of the clearance would be volume over time. And as we are considering according to this that the volume is constant, then the clearance of the drug is constant too under first order kinetic. Okay, so we will talk a little bit about the way that we or the calculations or equations that we use to determine the clearance, either total clearance or not. And we will start with the simplest way, which is, again, this is clearance, which is total clearance, okay, or systemic clearance. One way to determine the clearance of the drug is using multiply to the volume distribution. Okay, we know that the unit of volume distribution is volume for sure. The unit of K is 1 over time. And again, we are talking here about first order kinetic or linear kinetic for sure. So this unit of the clearance would be volume over time. We know that this is constant under first order kinetic, and we know this is constant for sure. So by default, this would be constant, right? So we can determine the total clearance by knowing the rate constant, elimination rate constant, and the volume distribution. And we already know how to determine this, right? If you don't know, just review our previous videos related to the elimination rate constant. Okay, so another way to define the clearance. Oh, before going into another equation, we need to emphasize on one point, which is if this is total clearance, then this is the total elimination rate constant. Okay, and we mentioned before that K equals the sum of all the processes that we have in elimination, the rate constant, constants of different processes that we have in elimination, because this is elimination rate constant, right? Which is having the overall elimination process. So if we are talking about first, I will keep just repeating that we are still talking about first order kinetic, because when we are not having first order kinetic, we will have different way of dealing with the kinetics, okay? So the elimination rate constant will be the sum here, the sum of all the constants of different processes that each one of them is first order or following first order. So it would be K excretion plus K metabolism, okay? And each one of them is the sum of all the, in this case, the excretion processes, which could be in the bile, could be in feces, could be in the milk, any constant that is related to different tissues or different pathways would be involved, and they are excretion constant. Or it could be related to metabolism, which may happen in each and every organ, but we are more concerned of whatever is happening to the drug that we are testing. So it could be an hepatic, could be even metabolism in the renal, right? Or could be, let's say, cellular level, such as in the GI. And again, all the constants that is related to those processes would be involved. So K, which is the total elimination rate constant, would be the sum of all the processes that the constant of all the processes, kinetic processes involved in this. And again, under first order kinetic. Okay? If we know this that we already mentioned earlier, and we know this equation, can we accordingly, by knowing this one and this one, can we determine the metabolic clearance or the excretion clearance, knowing both of those equations? Yes, we can, because again, under first order kinetic or linear kinetic, the metabolic clearance would be equal to, again, it's constant multiplied to volume distribution, but as this is metabolic clearance, this would be metabolic rate constant, right? We need to use the constant that is related to the clearance that we are measuring, okay? So if this is metabolic, then this would be metabolic. If we want to determine the excretion clearance, this would be again rate constant multiplied to VD, but this, as this is excretion clearance, this would be excretion rate constant. Okay, and for sure, the volume distribution is constant in the model that we are dealing with, right? So the unit of the volume distribution is volume. The unit of each one of those is 1 over time because it's first order kinetic. So 1 over time for the constant that we are having that following first order, and the unit of each one of those is volume over time because it's clearance and it's following first order kinetic. Okay, so there is a way, yes, according to what you know, but just use the right rate constant that you are having. So another question, can we determine the, sorry for that, can we determine the fraction excreted of the drug or fraction metabolized of the drug according or if we are considering that K, Km, Ke, or total clearance, metabolic clearance, and excreted or excretion clearance. Can we, again, if we remember that the fraction in general is part over total, and we need to use the related part to the related total, right? We need to have both of them. If we are talking about, again, excretion, a fraction, I need to use part that is related to excretion. So the part in terms of rate constants, okay, I can use Ke, which is the part, and the total is K, which is the rate elimination rate constant. Okay, if I want to have fraction of metabolism, this would be, again, if I want to have it in terms of constants, I will have it as K metabolism over the rate constant of elimination. So just use the right term that you want to define. Okay? can we use another way? Let's say if we are using a clearance terms. So using clearance or clearances, I can determine the fraction of excretion and the fraction of metabolism. Again, I want to use clearances, so I will use clearances as terms, but again, the total would be your total clearance, which describing the whole or overall elimination process, either excretion or metabolism. But if I want to have excretion fraction, so I will have excretion clearance. If I want to have metabolism, so I need to have metabolism. So just use the right term, okay? And again, if you just remember that the clearance is K multiplied to VD, okay? So this would be Ke multiplied to Vd over K multiplied to Vd, right? And this is constant, so I will have it as Ke multiplied over K, over K. And similar thing to here, which would be equal to Km over K, right? So those are the fractions, and for sure the fractions are unitless because we are having similar terms on both sides, okay? And if I want to have them in percentages, let's say the percentage of drug excreted or the drug metabolized percentages, you need just to multiply with 100, okay? So according to whatever we just mentioned, we can, again, clearance under first order kinetic, we can have it using one way, which is K multiplied to VD, or each one of them using the right rate constant if we want to have the metabolism clearance or the elimination, the excretion clearance, okay? Another way of determining the clearance is by knowing that the clearance, total clearance, would be equal to the rate of elimination at certain time over the measured concentration and the plasma at certain time. Okay, let's just have it by rate of elimination, which is at certain time that would be equal to total clearance multiplied to the concentration at certain time. Okay, this is total clearance. Okay, and this is elimination. Okay, so accordingly, this is for sure okay, and this is mass over time. So accordingly, if you just determine the unit of this, you'll find the unit of that. Okay, and just make sure that you, according to the concept that we just mentioned, you will able to determine the excretion clearance and the metabolic clearance using this equation, right? Can you? Yes, we can. Concentration at certain time equal the rate of what? Excretion at certain time, at certain time. If we want to determine the metabolic clearance, this would be rate of metabolism at certain time, because this is a clearance, metabolism clearance. So just make sure that you are using again the right term or the right rate to determine the right clearance. Okay, so if according to this equation, if I want to sketch, let's take this equation, okay, which is rate of elimination. Oops, why this is happening? Elimination, okay, equals at certain time equals total clearance multiplied to concentration at certain time. I want to sketch this relationship. And again, we are still under linear kinetic. Okay, so rate of elimination, we will have it as E, capital E, okay, to just differentiate it from the excretion. So this is elimination versus concentration at certain time. So we are having this as our y and this is as our x. And again, we are still talking for sure about first order kinetic. According to this equation, what would be the profile that we are having? This would be our profile, okay, which by the way, you know, for for, uh, for sure. And at this point, if you are having first order kinetic, and just go and review whatever that we have in the introduction of the IB bolus or in the class of the rate orders, that if you have rate versus concentration or amount of the drug, we will have linear kinetic if we are talking about first order kinetic, right? It's the same thing. I didn't change anything. I just mentioned that elimination rate constant versus concentration, which is the same as here, but we are talking about this equation, which is showing us whatever is happening in the first order kinetic. And the only addition information that you know, again, we are talking about first order kinetic, that, okay, you know that you will have linear profile for sure, it's first order kinetic, but the slope here would be equal to your total clearance. Okay, and again, just make sure that you are drawing elimination rate constant to have the total clearance. So I will ask you a question here and sketch it by yourself. If I want you to sketch rate of metabolism of the drug versus concentration measured at certain time, and here at certain time, and or rate of excretion at certain time versus concentration measured in the plasma, the concentration of the drug measured in the plasma at certain time. And again, we are still talking under first order kinetic. What would be the profile here and here? What you should know now, and what would be the slope here and the slope here. And again, don't forget, this is metabolism and this is excretion, not the overall elimination. Okay? Just think about it and do it by yourself. If for now, we have for the total clearance, we were able to define it or determine it by having K multiplied to VD. We also have it as rate of elimination over concentration measured in the plasma. Okay, there's another way to determine the clearance, again, total clearance, which would be equal to dose if we are talking about IV bolus, first order kinetic. So we are still talking about IV bolus, okay? And this would be equal to x over area under the curve total. So this is the initial amount of the drug, which is, if you are talking about IV bolus, is the dose, okay? And this is total area under the curve. And by the way, we will talk about this in details in a couple of classes. And again, it's another way to determine the clearance if you know those terms. This is the dose that you are giving, so we will talk about how to determine total area under the curve. But for now, just know that we can determine total clearance by knowing the dose and total area under the curve. We know that clearance is K multiplied to VD, right? So can we determine VD using this equation? Yes, we can, which would be equal X multiplied to K over dose over K multiplied to area under the curve. This is again the dose, this is area under the curve. For now, just take it as it is. And K, we were determining K using the slope of the equation that we have, the model equation, depending on whatever the profile that you are using, okay? So on this class, we had so many information related to the clearance in general, and more specifically for IV bolus. We were talking about first order kinetic. We know that for now, or until this point, for first order kinetic or linear kinetic, you know that we have different parameters that are constant. Examples, we have half-life, right? First order kinetic. We have K, which is first order elimination rate constant, or any of the rate constants that are following first order kinetic. And we know that VD under first order kinetic is constant, and we know that total clearance or any of the clearances of the drug following a first order kinetic are constants. So those are the major parameters that we usually use to define the first order kinetic in IV bolus one compartment model. Okay, for the clearance, we were using different equations to calculate it or to measure it. We have clearance equals K multiplied to VD. We have K that is equal rate of elimination over concentration. We have clearance that is total, that equals the sum of all the clearances that we have, metabolic or excretion, and we have clearance that is total equal amount over total area under the curve. And we will stop it here at this point. We will stop here at this point, and we will continue in our next class.